Throughout railway history, some of the most powerful and innovative locomotives were permanently withdrawn from service after just a few years. Today, we're exploring 7 machines that were deemed too problematic to ever run again. The development of railway technology has always been a story of bold experimentation and learning from mistakes. Engineers and designers constantly pushed boundaries, trying new concepts and technologies in the pursuit of better performance, greater efficiency, and increased power. But not every experiment succeeded. Some locomotives had flaws so fundamental that railway authorities decided they could never safely or economically operate again. These are the stories of 7 such machines. Number 7. The Fury, London Midland and Scottish Railway's Hypershore experiment in 1929. The London Midland and Scottish Railway embarked on an ambitious project to develop a Hypershore steam locomotive that would set new standards for efficiency. The result was a locomotive initially numbered 6399, but more commonly known as Fury. This machine was designed to operate at extremely high boiler pressure, using innovative technology that had never been attempted on such a scale. The engineers behind Fury believed that by dramatically increasing boiler pressure, they could extract significantly more work from each pound of steam generated. The locomotive was fitted with a Hypershore Schmidt boiler operating at 900 pounds per square inch, nearly double the pressure of conventional locomotives at the time. This required special materials and construction techniques, making Fury one of the most technically advanced locomotives of its era. Testing began in 1930, and initial results seemed encouraging. However, the extreme pressures involved created unprecedented challenges. The boiler tubes and fittings were operating at the very limits of available materials technology. Maintenance proved extraordinarily difficult, as even small leaks could be severe at such high pressures. The locomotive required constant attention and specialized knowledge that most railway workshops simply didn't possess. Then, during a test run in 1930, tragedy occurred. A boiler tube failed catastrophically, releasing superheated steam at 900 pounds per square inch. The crew member in the fireman's position suffered fatal injuries from the escaping steam. This incident shocked the railway industry and raised serious questions about the viability of ultra-high-pressure steam technology. Following a thorough investigation, railway authorities concluded that the risks associated with such extreme pressures were unacceptable. The materials and engineering knowledge of the time were simply insufficient to safely operate boilers at these pressures. Fury was withdrawn from service immediately and never operated again in its Hypershore configuration. The locomotive was later rebuilt with a conventional boiler and renamed, but the original Hypershore Fury was gone forever. This incident effectively ended British experiments with ultra-hypershore steam locomotives and served as a sobering reminder that technological ambition must be balanced with safety considerations. Number 6. The Bull-Eyed Leader Class. In the late 1940s, Oliver Bull-Eyed, the chief mechanical engineer of the Southern Railway, developed one of the most unconventional steam locomotives ever built in Britain. The Leader class was designed to combine the efficiency of steam power with the operational flexibility of diesel locomotives. The result was a machine that looked unlike any steam locomotive before it. The Leader featured a completely enclosed design with driving cabs at both ends, eliminating the need to turn the locomotive at the end of each journey. The boiler and machinery were housed in a central section, with the crew protected in comfortable, fully enclosed cabs. On paper, this design offered numerous advantages, including better working conditions for crews, reduced turnaround times, and improved visibility. Construction of the first Leader began in 1948, and it was completed in 1949. However, problems emerged as soon as testing began. The enclosed design, while protecting crews from weather, created a new problem: inadequate ventilation. The machinery spaces became unbearably hot during operation, with temperatures reaching levels that made maintenance work nearly impossible. Components located in these hot zones suffered accelerated wear and frequent failures. The riding qualities of the Leader were also disappointing. The unconventional design created vibration and rough riding that made it uncomfortable for crews. The complex chain-driven mechanism that transmitted power to the wheels proved troublesome, requiring frequent adjustment and repair. Reliability was poor, with the locomotive spending far more time under repair than in service. Perhaps most critically, the Leader's performance failed to justify its complexity and cost. Despite all the innovative features, it couldn't outperform conventional steam locomotives that were simpler and cheaper to build and maintain. By 1950, with British Railways already committed to desalination, continuing with the Leader project made little sense. Only one Leader was completed, and it operated for barely a year before being permanently withdrawn in 1950. 4 more were under construction, but were scrapped incomplete. The single completed locomotive was stored for a few years before being cut up for scrap in 1952. British Railways concluded that the design was fundamentally flawed and offered no advantages worth pursuing. The Leader remains one of the most unusual and unsuccessful locomotive designs in British railway history. Number 5. The Kitson-Still locomotive. In the 1920s, engineers were exploring ways to combine the best features of steam and internal combustion engines. The Kitson-Still locomotive, built in 1927, represented one of the most ambitious attempts at creating a hybrid power plant. This unusual machine was designed to operate as both a steam locomotive and a diesel locomotive, theoretically offering flexibility and efficiency. The Kitson-Still used a unique double-acting engine design where steam and diesel combustion occurred in the same cylinders. At low speeds, the engine operated primarily on steam. As speed increased, diesel fuel was injected, and the engine transitioned to diesel operation, with steam providing assistance. The designers believed this would provide the best characteristics of both power sources. The theory was fascinating, but the practical execution was deeply problematic. The engine was extraordinarily complex, requiring precise coordination between the steam and diesel systems. Maintenance personnel struggled to understand and service the unusual machinery. The engine required different fuels, lubricants, and maintenance procedures, depending on which mode it was operating in, creating confusion and errors. Performance testing revealed that the Kitson-Still failed to deliver on its promises. The transition between steam and diesel operation was rough and inefficient. The engine consumed more fuel than a conventional diesel locomotive while producing comparable power. The complexity of the dual fuel system meant that reliability was poor, with frequent mechanical issues affecting both the steam and diesel components. The locomotive operated for only about 4 years, spending much of that time under repair or modification. Engineers attempted various fixes, but the fundamental design was simply too complicated. By 1931, it was clear that the Kitson-Still concept was not viable for railway service. The locomotive was withdrawn and eventually scrapped in 1935. No other locomotives were built to this design, and the hybrid steam-diesel concept was abandoned. The railway industry concluded that specialized locomotives, whether pure steam or pure diesel, were more practical than attempting to combine both technologies in a single machine. The Kitson-Still stands as an interesting technological dead end in locomotive development. Number 4. The Biograt oil burning experiment for London transport in the 1920s. London's Metropolitan Railway needed powerful locomotives to haul heavy commuter trains through the increasingly congested underground sections. The railway ordered a specialized Biograt articulated locomotive, but with an unusual requirement. It had to burn oil fuel rather than coal to reduce smoke and pollution in the tunnels. The locomotive, delivered in 1925, was a massive articulated machine with separate engine units at each end and the boiler suspended between them. This configuration provided tremendous power while allowing the locomotive to navigate the tight curves of the Metropolitan Railway. The oil burning system was designed to provide cleaner combustion than coal, making it more suitable for underground operation. However, the oil burning system created unexpected problems. The burners were temperamental and difficult to adjust properly. When not perfectly tuned, they produced excessive smoke and soot, defeating the entire purpose of using oil fuel. The intense heat from oil combustion also caused maintenance issues, with fireboxes and boiler tubes suffering accelerated wear. Operational costs were another significant concern. Oil fuel was expensive, and the locomotive's consumption was higher than anticipated. The complex burner system required specialized knowledge to maintain, and few railway workers had experience with oil-fired locomotives. Training was expensive and time-consuming. The locomotive also proved to be too powerful for its intended service. The tremendous tractive effort it could develop was rarely needed on the Metropolitan Railway's routes. And operating such a large locomotive for relatively modest trains was economically wasteful. The articulated design, while allowing it to navigate curves, made it longer than conventional locomotives, creating operational difficulties at stations and yards. After just a few years of unsatisfactory service, the Metropolitan Railway decided to withdraw the locomotive. By 1930, it was clear that the oil-burning Garratt was not suitable for their operations. The railway converted it to coal-burning and sold it to another operator. But the original oil-burning configuration never ran again. This experience demonstrated that technological solutions must be matched carefully to operational requirements, and that complexity doesn't always equal improvement. Number 3. The experimental turbine-electric locomotive. Union Pacific GTEL. First generation, while Union Pacific's later gas turbine locomotives achieved some success. The railroad's first experiments with turbine technology in the late 1940s were far less fortunate. The initial prototype turbine-electric locomotives revealed problems that took years to address, and some early units were permanently withdrawn after brief service. These early turbines were designed to provide immense power for hauling freight across Union Pacific's western routes. The gas turbine engine could produce far more horsepower than contemporary diesel locomotives, making them attractive for heavy freight service. However, the technology was still experimental, and numerous issues plagued the early designs. Fuel consumption was the most obvious problem. The turbines burned bunker sea fuel oil, a thick, heavy residue left over from petroleum refining. While this fuel was cheap, the turbines consumed it at extraordinary rates. Even with low fuel costs, operating expenses were concerning. The turbines were only economical when hauling the heaviest trains at sustained high speeds, a fairly narrow operational window. The turbine engines were also extremely loud, creating noise levels that were uncomfortable for crews and nearby residents. Maintenance was complicated by the high temperatures and stresses involved in turbine operation. Components wore rapidly, and specialized knowledge was required for repairs. Many mechanical parts were unique to these locomotives, meaning spare parts were expensive and not readily available. Early reliability problems were severe. The turbines were sensitive to fuel quality, and contamination could cause rapid deterioration of turbine blades. Starting the turbines in cold weather proved difficult, and the units often failed to operate properly in winter conditions. Several of the early prototype units spent more time under repair than in service. Union Pacific eventually developed improved turbine designs that addressed some of these issues, but the earliest experimental units were deemed beyond economical repair. Several were permanently withdrawn after only a few years of sporadic service. These early failures taught valuable lessons, but they also demonstrated the challenges of introducing radically new technology to railway operations. Number 2. The Sentinel Camel steam railcar in the 1920s and 1930s. British railways experimented with steam railcars as a way to reduce costs on lightly used branch lines. The Sentinel Camel Company developed several designs, but some of their more experimental units proved deeply problematic and were withdrawn after brief service. These railcars combined a small vertical boiler, a high-speed steam engine, and passenger accommodation in a single vehicle. The concept was to provide economical service on routes where full-size trains were unnecessary. The vertical boiler design was compact and efficient for its size, and the high-speed engine could propel the railcar at respectable speeds. However, several design issues made some Sentinel railcars unpopular and ultimately unworkable. The ride quality was often poor, with vibration from the engine and rough suspension making passenger travel uncomfortable. The vertical boiler, while space-efficient, was difficult to maintain and prone to steaming problems. Water capacity was limited, requiring frequent stops for refilling. Some experimental variants incorporated unusual features that proved impractical. Articulated designs intended to increase capacity were structurally weak and suffered from cracking and frame failures. Attempts to increase power by using larger engines made the rail cars too heavy, causing excessive wear on tracks and increased fuel consumption that negated the economic advantages. The most problematic units suffered from persistent mechanical failures. Steam leaks, engine troubles, and boiler issues kept them out of service frequently. Operating departments found them unreliable and difficult to maintain with standard railway facilities. The specialized knowledge required to service these unusual machines was often not available at smaller depots. By the mid-1930s, several of the more experimental Sentinel railcar designs had been permanently withdrawn. Railway companies concluded that these particular variants were not worth the trouble of keeping them running. Some were converted to other uses or scrapped. While railways focused on more conventional railcar designs or increasingly on diesel-powered alternatives, the failures of these experimental steam railcars helped accelerate the transition to diesel railcars on British branch lines. Number 1. The South African Railways Experimental Condenser Locomotive. Our final entry comes from South Africa, where the challenging operating environment of the semi-arid Karoo region inspired unusual locomotive designs. In the 1950s, South African railways experimented with condenser locomotives intended to operate in areas where water supplies were scarce. While some condenser designs worked reasonably well, certain experimental variants were spectacular failures. The concept behind condenser locomotives was straightforward. Instead of exhausting steam to the atmosphere, it would be condensed back to water and reused. This would dramatically reduce water consumption, allowing locomotives to operate long distances without refilling. For water-scarce regions, this seemed like an ideal solution. The experimental units featured massive condensing equipment with enormous radiator-like structures mounted on tender cars behind the locomotive. Fans drove air through these condensers, cooling the exhaust steam and converting it back to water. In theory, this should have allowed almost indefinite operation without taking on water. However, the practical challenges were immense. The condensing equipment was extremely heavy, significantly increasing the weight the locomotive had to haul. This reduced efficiency and limited the loads that could be pulled. The complex plumbing systems connecting the locomotive to the condensing tender were prone to leaks, and maintenance was difficult and time-consuming. The condensers also proved unreliable in service. Dust and debris would clog the condensing elements, reducing their effectiveness. In hot weather, when they were most needed, the condensers struggled to cool the steam adequately. Water quality issues caused scaling and corrosion in the complex piping systems. The additional equipment required specialized maintenance that many depots couldn't provide. Perhaps most problematic was that the condensers only worked well under very specific conditions. At low speeds, or when working hard on steep grades, the condensers couldn't keep up with steam production. The locomotives would lose water rapidly, defeating the entire purpose of the system. The complexity and weight penalties meant that even when the condensers worked properly, the locomotives were less efficient than conventional designs. After several years of disappointing results, South African railways withdrew the most problematic experimental condenser units from service. While some later condenser designs proved more successful, these early experimental variants never ran again. They were eventually scrapped, their complex condensing equipment salvaged for parts. The experience taught valuable lessons about the practical limits of water conservation technology and the importance of reliability over theoretical efficiency. These 7 locomotives represent important lessons in railway engineering history. Each was designed with genuine hope that new technology or innovative design would provide. Advantages over conventional locomotives. Engineers and designers invested tremendous effort and resources into these projects, believing they were creating the future of railway transportation. Yet each of these machines ultimately failed to live up to expectations. Some suffered from fundamental design flaws that became apparent only during operation. Others were simply too complex, requiring maintenance and expertise that railway operations couldn't practically provide. Still others were overtaken by technological change, becoming obsolete before they could prove themselves. The permanent withdrawal of these locomotives wasn't merely about admitting mistakes. In each case, railway authorities carefully evaluated whether problems could be fixed economically. When the answer was no, the difficult decision was made to cut losses and move forward with more promising technologies. These failures contributed as much to railway progress as successful designs. Engineers learned what didn't work, helping them avoid similar mistakes in future projects. Safety standards were strengthened based on lessons learned from problematic designs. Economic analysis became more sophisticated, helping railways evaluate new technologies more realistically. Today's reliable and efficient locomotives stand on the foundation of both successes and failures. Every withdrawn locomotive, every abandoned technology, taught the industry something valuable. While none of these 7 machines survived to become success stories, their contributions to railway knowledge were significant and lasting. Thank you for joining us on this exploration of railway history's most interesting failures. These stories remind us that progress requires experimentation, and that learning from mistakes is just as important as celebrating successes.